So, this relative ratio of the time scale of interest and the material relaxation time is called Deborah number, and so we quantify the material response time using this relaxation time, and of course we always have a time scale of interest which could depend on an engineering application, it could depend on what is the material we are studying and so on. For example, for a structural application we are looking at 30 or 50 years of lifetime, and so that is the time scale of interest. Sometimes when we are processing something, let us say injection molding of polymer objects like a plastic, let us say an optical disc or a CD or a DVD, then in those cases we are looking at extremely fast production rates, and some time scales we are interested in are milliseconds and so on. So, therefore, time scales of engineering application vary, and so that is why that is something that varies, and so the ratio of these two can tell us what may be the material response. And for example, if Deborah number is less than 1, which implies that relaxation time is close to 0, or the experimental time scale or time scale of interest is very large, geological time scale, then in that case definitely relaxation process would lead to dissipation of energy. So, either of the two, either the relaxation times are very small or our length time scales of interest is very large, and opposite is true. If Deborah number is very large, that would be the case when either the relaxation process is very slow, the relaxation times are very large, or our time scale of interest is very small. So, in that case we would see that the relaxation process would actually lead to storage of energy. Okay. So, in this case the what we saw earlier, the deformation of atoms can lead to dissipation only if defect also move, otherwise it will not lead. But if we wait millions of years, then certainly at those rates defects will move, and therefore we will have dissipation. So, just to now look at the overall aspect quantitatively, we will look at Maxwell model, and Maxwell model is basically given by the stress being related to stress rate and strain rate. So, that is what I meant when we said viscoelasticity, we will have different variables which may be interrelated to each other. We are using this subscript just to imply that we are using simple shear as our mode of deformation, and we are looking at only one component of stress and one component of strain rate. We know overall that in a material there are 9 components, and given that stress is symmetric there are 6 components, and similarly 6 components of strain rate also. So, to completely specify the state of the system we will need to solve for all of these, but given that we are subjecting the material to only simple shear, we only have these are the relevant ones. So, therefore, we will continue to use these subscripts, even though many times people will try to describe these things just as a model like this, right. You could use this also to describe a Maxwell model, but we are just making sure that we will always remind ourselves that we are looking at a specific situation, and this is the statement of Maxwell model which is valid for simple shear. In general, the overall Maxwell model which is valid for 3 dimensions we will write down later on. And you can see that if lambda is 0, then tau yx is nothing but eta gamma dot yx. So, that is nothing but Newtonian fluid. And similarly, when lambda is very large, what we have is this term and this term dominates over this term, and so only these 2 terms are present, and this can be visualized as gamma dot yx is nothing but del gamma yx by del t. And again we have already said this multiple times before that this is valid only when deformations are small, right. In general rate of strain is not same as strain rate tensor, right. We will need to find the convected rates of strain to get strain rate, but given that deformations is small and we are going to only look at linear viscoelasticity for now, this relationship is fine. So therefore we have lambda del tau y x by del t is same as eta del tau y x by del t, and since the two derivatives are related to each other for any arbitrary amount of time, we have basically the tau y x itself equal to eta by lambda gamma y x. So which is nothing but an elastic, that stress is proportional to strain, and so this is the other parameter which we use to characterize the Maxwell model. So Maxwell model is a 2 parameter model, lambda and eta or lambda and g, and lambda is the relaxation time. So we have already seen that when relaxation is 0, relaxation time is 0, material behaves like Maxwell model reduces to viscous fluid. When relaxation time is large, it behaves like an elastic solid. So it combines both viscous and elastic responses phenomenologically. It says that this is the relationship for fluid, it says this is the relationship for elastic solid. Let me combine the two, and therefore I will get viscoelastic response.
Many a times mechanical analogues are used to describe the viscoelastic models. These serves as representations of how viscous and elastic response is combined in a given model. For example, Maxwell model is a series combination of spring, which represents elastic response, and a dashpot which represents viscous response. These analogues are also useful to understand how to arrive at different terms of a given model. Just the way a complex circuit, the electric circuit, can be simplified by realizing current or voltage going through different resistances and capacitances, we can simplify mechanical analogues by analyzing how stress and strain are subjected to in these different springs and dashpots.
What you will see is strain of elastic element plus strain of viscous element is the overall strain. Yeah, and with this, if you put together, then you have the Maxwell model of viscoelasticity. So now let us define another mode of mechanical deformation, which we will call stress relaxation. So stress relaxation is an experiment in which we apply a constant strain on the material. So we apply gamma y x, a constant strain, and by this superscript 0 we indicate that it is a constant value, it does not change as a function of time, and so this is called a stress relaxation experiment. So what we have is we take a material and at time t is equal to 0 we basically apply a strain which is constant, and this is what we have discussed already in the previous class, that when we apply a constant strain, what happens to an elastic or a viscous material. Now we can try to understand what happens to a viscoelastic material by just looking at the response of Maxwell model itself, and since gamma y x is constant, the governing equation for Maxwell model will be lambda del tau y x by del t is 0, right. So it is an ordinary differential equation, and the solution of this is an exponential, and the initial condition we can write that at time t is equal to 0 stress response is completely elastic. So whatever deformation that is put, and the g, which is a parameter which describes the elastic response of a Maxwell model, that is the amount of stress which is required in the initial at time t is equal to 0, and with time, because of the solution of this, what we find is with time the stress decays. There is a stress decay in the material, and therefore, what you would see is stress goes down, and this is called a stress relaxation phenomenon. So, the amount of stress that is required to hold the material in the new deformed state decreases as a function of time, and the rate at which this happens is characterized by lambda. If lambda is 0, then this will be 0, right, stress will be immediately 0. If lambda is very large, then basically you have this quantity becoming 1, and therefore, then it is an elastic response. So, Maxwell response clearly of course has both the terminal responses. The reverse can also be done by changing the time scale at which I do the stress relaxation experiment. I can do the stress relaxation experiment for a millisecond, then for many materials I will observe that all the energy is stored and nothing is relaxed, or I can do the stress relaxation experiment for years, then I will see that many solid like object which appear to be solid like seem to actually relax stress, and there is some plastic or other contributions which lead to energy dissipation in the material.
Something called yielding.
Yielding, yeah. So, in case of crystalline solids, yielding is the threshold of deformation beyond which the plastic deformation, the mechanisms which lead to plastic deformation take place. But what we are talking about here is the deformation is still small, but since we are waiting long enough, that can happen. So, the processes which may happen during yield at normal rates may happen over years at small deformation. So, let us say if 4% is the strain beyond which plastic deformation happens, if I deform the material to 2%, I would expect nothing to happen, right, it is elastic. But if I wait years and years, then with the grain boundary and grain boundary deformations and all that, those things which happen during plastic deformation will happen over much longer periods. So, that is why then material will relax at very long time scales. And so, that is what is summarized here, that when lambda is 0 for a perfectly viscous fluid, the decay is instantaneous, which means stress is relaxed away immediately, instantaneous dissipation. For a perfectly elastic solid, no decay is observed. And so, this is what is the stress response. For a constant step input of strain increase, we have stress basically decreasing exponentially. And we can sort of think of this in terms of macromolecule, right, because it is always helpful for us to think in terms of microstructure molecular mechanisms. That is one of the important things for rheology. So, let us say if we have a solution of polymer molecule and then now we are applying a strain on it, right. So, what do we mean by stress relaxation? So, if it is only water molecules, then what happens is instantaneous decay, but now because we have a macromolecule which has other relaxation processes possible, which means the segments can move, the overall molecule can also move. So, what we have is, so if I apply this a small deformation, this molecule will get extended at instantaneously, right. So, the spring and dashpot that we had visualized earlier, it will be longer as opposed to, so it suddenly got stretched. But over time what happens is, since the segments, since there are fluctuations present in the material and molecular flexibility, segmental flexibility is there, this particular molecule in the new state, which is the deformed state, will again occupy the same spherical conformation. So, which means it will come back to same length. Of course, its orientation may also continuously keeps on fluctuating. So, that is why this what we can say is the macromolecule is able to relax through segmental relaxation and other modes which are present. So, the macromolecule is undergoing mechanical relaxation because of its segments can move, there is bond rotation around the macromolecular chain, and because of these things this molecule which got stretched at 0 time is able to come back to equilibrium state. So, now a new equilibrium stress free state is again obtained. Yeah.
We call it equilibrium state or steady state?
In this case it is an equilibrium state, right.
But you told some fragment may fluctuate.
No, fluctuation does not imply non-equilibrium, right. A jar of water with its random molecules fluctuating is not a non-equilibrium state. The fluctuations at molecular scale in fact are no indication of its non-equilibrium nature, right. With those fluctuations material is at equilibrium, only at molecular scale fluctuations are there. On the average when you look at average velocity is not present, there is no temperature non-uniformity, there is no pressure non-uniformity and so on. So, any macroscopic variable there are no gradients or they are not changing as a function of time, but if you look at individual molecule or individual bond they are always fluctuating. Only at temperature 0 all these fluctuations will die away, right. So, therefore,
Fluctuations do not imply non-equilibrium state.
Because fluctuations whenever we say we are talking molecular scale phenomenon. So, to define equilibrium what we should do is find average of those fluctuations, right, because if we are applying a constant stress, the fluid will continue to keep on, the molecules will continue to see, the molecules in a fluid, in a gas or a liquid are not really in energy minimum state, right, they are fluctuating. Thermal energy is sufficient for molecules to move about. So, therefore, when you apply a force and a stress, molecule can continue to move.
If we remove the stress,
then it will come to a halt. Yeah, equilibrium again, which is a new equilibrium state.
Yes,
And the only fine point which we have not specified, but it is important to mention is that in the process there was some mechanical energy which was input into the system and that has dissipated. So, the temperature between this and this will be slightly different, and that is what, if we keep on stirring for a long time then the fluid temperature will of course go up, right. So, the mechanical energy has been converted to the internal energy, thermal energy. So, the average temperature may go up, but many of the cases when we are doing these flows we are either controlling the temperature or the amount of viscous dissipation may be minimal. So, therefore, we are just saying that this is an equilibrium state and this is also an equilibrium state. It may not be exactly the identical equilibrium state, there may be a small difference in both the equilibrium states, but they are both equilibrium states because in this condition also average velocity is 0, there are no temperature gradients, there are no pressure gradients, everything, while when you apply a constant stress there is a velocity gradient in the system, and therefore that is a non-equilibrium situation. So, any time either temperature gradient is there, velocity gradient is there, concentration gradient is there, these are all non-equilibrium transport phenomena. Yeah.
So, the flexibility story of compressible fluid will be different or will be remain same?
What is that?
In compressible fluid.
Huh.
It is case of incompressible.
Yeah, no, so compressible and non-compressible fluids as far as viscous flow and dissipation is concerned are similar. In that case only thing is the pressure is also another variable. In our case we are never discussing pressure as, so I am only saying temperature will be different in two cases, right, but in compressible flow pressure is also another variable. But from a molecular standpoint, from the point of view of relaxation processes, incompressible and compressible fluids will have similar features. They will have viscous response only, dissipative response only. So, at time t is equal to 0 is this stress that we talked about, right. So, therefore, any viscoelastic material initially will show an elastic response. So, if let us say I do the same experiment and observe it for a microsecond, then I will see only response like this, and then I will say, oh, macromolecular solution is almost elastic. But if I do the same experiment over seconds or minutes, then I will say that, oh, the energy is all dissipated, the molecule actually got deformed, but it came back to equilibrium state, and therefore it dissipated the energy away. So therefore, by doing stress relaxation experiment, I can probe what is the relaxation process present in the material. I can do my stress relaxation experiment at for different times and characterize this lambda, and quite often what will happen is I will have the overall stress relaxation like this, and this may not be, it may not be possible to fit to a one relaxation time, one exponential process. If I try to fit, let us say, exponential curve to this, it may happen that I will get a fit like this, or I will get a fit like this, right, if I try to fit exponential curve. So what does this imply? What would this imply if I, so in the graph here I am showing is a nice exponential, this is actually an exponential decay, but let us say if the experimental data was like this, the way I am showing, or experimental data, then you will not be able to fit one particular exponential to it. So what does that imply? Based on Maxwell model, each and every relaxation process which is characterized by one relaxation time should give us exponential decay, but combinations of exponential can be actually. So therefore I can try to fit multiple exponentials, and then I will say that, oh, looks like the material that I am studying has in fact multiple relaxation processes, and if I assume, then I have to look at, of course, the material makeup, I will have to make a hypothesis of what might be the relaxation processes, and I will know that, oh, there are some bond level or segment level phenomena, so that will be less time scale. Then let us say if it is an entangled polymer melt, the way we discussed, polymer molecules are entangled, so therefore they will be very slow relaxation processes. So then I can clearly see, by studying stress relaxation, I can try to see what are the relaxation times or relaxation modes which are present in the material. And we should remember that all of this we are doing at constant strain and also strain value which is small. Okay. So to do this quantification effectively, what we do is we define a material function called relaxation modulus. So which is defined here, so this is a material function which is done when a step strain input is given or step strain perturbation is given to a material. At time t equal to 0, a constant strain is applied and stress is measured. We should remind ourselves that, of course, how this measurement is done will depend on which geometry, right, and so on. And then the relaxation modulus is defined as G of t stress divided by gamma. So in this case, therefore we are not evaluating one constant, right, the whole curve itself is an indication of the material response. If I get an exponential curve, right away I know, oh, this is good, this material has one relaxation process, and I can also say what is its relaxation time. But in general, most common materials we will find will not be able to fit one exponential, and then it is our job to try to find out what is the meaning of multiple relaxation processes that are there in the material. And so all of this is of course also very important in terms of the amount of deformation. The stress relaxation modulus, right, which we can write here is G of t is equal to G e to the power minus t by lambda. So it is independent of the strain amplitude. right. So, whether I apply 1% strain or 0.5% strain does not affect the relaxation modulus. So, I am characterizing the material response using a linear regime, and that is where I said earlier that the overall equilibrium structure of the material is sufficient to describe the phenomena. So, if I apply 0.5% or 1% strain, both the cases the responses can be captured using this relaxation modulus. We will see that for nonlinear viscoelasticity, G will be a function of time and the strain amplitude that was applied on the material. Because we are taking the material far away from equilibrium, its new structure is also relevant in determining how far away from equilibrium you have taken. And so, the relaxation modulus itself will be a function of strain amplitude itself. Okay, so, we are only looking at linear amplitude, and therefore, G of t is not a function of gamma y x. Secondly, just the way I can think of overall stress response as combinations of several, I can also do experiments where I put one strain and after some time I put another strain, and I should be able to actually get the overall response by just summing. So, instead of doing this experiment, now let me see if I can do this experiment. One strain and then I put another strain. So, I can individually do a solution for this, then I can do a solution for this, and I can add both of them together to give me what is the overall stress response. So, this is called superposition, right, which is again possible only because the material function is independent of the strain amplitude. The stress of course depends on strain amplitude, but it is a scaled output. If I double the strain amplitude, the overall stress also everything gets doubled, and so therefore, the relaxation modulus is independent of that strain amplitude. But in nonlinear regime we will see that that will not be the case. The stress will not be directly related to the strain in a linear way, right. So, there will be a nonlinear response.
Stress will remain same or not?
Where?
The superposition.
Yeah. So, the overall what we can do is I can do two experiments. I can do one experiment where I just apply this, and beyond a certain time I can do another experiment where I just applied this, and I can say that the overall response will be summation of this plus summation of this.
I am asking about stress. Stress will remain same. We are applying same stress or?
No, if you apply strain, then you measure stress, right. You do not you cannot control both of them at the same time. See, when I apply on an elastic solid, I apply a constant strain, I cannot again apply some stress, right. Stress will be determined based on the material. I cannot independently control both of them because both of them are related to each other through a proportionality constant. Do you follow?
Yes.
So, therefore, both of them are not independently controlled. In this case, strain is the one which is controlled and stress is what is being measured. So, what we are saying is the overall stress response can be a linear combination of responses to individual strains, and that is only possible because of small deformations. And so, okay, maybe we will stop here, beyond this we will do in the next class.